Welcome to our presentation and demonstration of our work titled Accelerating Search-Based Planning for Multi-Robot Manipulation by Leveraging Online Generated Experiences. Let's begin with the problem at hand. Considering a team of robot arms in a shared environment, we're interested in finding a set of collision-free, low-cost trajectories, one for each arm, from their start to goal configurations. Motion planning solutions for concurrent manipulation tasks will look something like this, where robots may move close to each other, but still not collide. In this example, the motions were generated using our proposed planner, which we call X-ECBS. We will introduce it shortly. When we first attempted to tackle these multi-robot planning problems with popular sample-based algorithms, we found that they struggled to scale, failing to produce any solutions for the 8-robot case, for example. Observing the difficulty in planning for all arms together, we turned our attention to multi-agent pathfinding algorithms that decouple the search. Now, in order to cast the multi-robot arm motion planning problem as a multi-agent pathfinding problem, we embed each arm's configuration space in a graph, where each node represents a configuration and each edge represents a feasible transition between two configurations. Under this construction, we can use algorithms like conflict-based search, or CBS, to resolve collisions between arms by imposing constraints on their graphs. In this simplified example, CBS finds collisions at time step 1 for robot 1, which we denote by a red circle, and imposes a vertex constraint there, denoted with a red square. It does so again for robot 1 at time step 2, eventually finding a collision-free solution. While CBS and its bounded suboptimal version xECBS are more effective, especially in terms of solution costs, they still cannot solve many of the problems that we're interested in. Let's look at one reason for why this is the case. Let's consider the configuration space of a single robot arm where a path is planned from its start to goal configuration. We can see that when a constraint is added to this robot search space, the new plan that respects this constraint is still very similar to the original plan. This would require many constraints to be added before a plan changes significantly. With that in mind, we propose to capitalize on the repetition within CBS and reuse past search efforts to inform future ones. Specifically, given a previously computed path, we keep it in the form of an experience. Then, when beginning a new search with a single new constraint, we can reuse valid parts from that experience. For example, when expanding the start state of the new search, the experience would be valid all the way up to the new constraint, and we can reuse it by adding it to the search frontier within an A* search, for example. As the search continues, every time a state that is part of the experience is expanded, we can again reuse the experience by adding another subset of it to the search frontier. By doing so, we are likely to explore a smaller portion of the search space and thus find the solution faster. This advantage is reflected in our simulated results in the form of higher success rates. Our algorithm, xECBS, is also provably complete and bounded suboptimal. Besides simulated experiments, which you are welcome to check out in our paper, we also tested our algorithm on real robot system with 3 Kinova Gen 3 robot arms. In a first set of tests, we tasked the robots with removing blocks from shelves, moving them to especially challenging configurations. Planning times were quick and the motions produced were visibly short. In a second set of tests, we repeated the same task but with simpler configurations that would more likely show up in real usage. Finally, we also demonstrated the flexibility of our approach by planning motions for the robots when holding excessively long objects. This did not require any changes to the algorithm or preprocessing of the space. For more details, please check out our paper. Thank you for your attention.